Okay, so let's travel back in time to regular languages. So to remind you, we had seen that every DFA can be converted into an NFA, and sorry, the other way around. Any NFA can be converted into DFA, and if you give me a regular expression, I can convert it into NFA, right? And I kind of hand-waved, I gave an example showing how to convert an NFA, or maybe it was a DFA, doesn't really matter, into a regular, I think it was a DFA. How to convert the DFA into a regular expression. I showed an algorithm, but by example. And those three things together implies that those three representations of regular languages are equivalent. Here, I would like to revisit the third thing that was hand-waved and present a more systematic algorithm that describes how it works. And very surprisingly, it's very similar in spirit to Floyd-Warshall. So what are we going to do? We're going to create various languages and then put them, we're going to define them recursively and then put them together, and in the end we will get the language of the wool automata, and we will do it in such a way that this algorithm can easily be converted into manipulation of regular expressions. So to this end, let Lij be the language of traveling from the ith stage to the jth stage. This is of course a regular language because, well, we can set the ith stage as start state and jth is the only accept state, and that will be the regular language of this automata. The language of M is of course just the union of all those languages going from the start state Q1 to stage I, where I, the ith state, is accepting. Here in this notation, by the way, notice that the automata, we use the regular 5-tuple notation, but the accept state is F instead of A. It's just because. Okay, now the idea would be that we will obtain a regular expression Rij for the language Lij, and then the regular expression for the language that we want would be just the OR of those, the regular expression, which is the OR of the regular expression for R1I for all the QI states that accept. Okay, so that's the plan. In the following Q1 to Qn, this would be the numbering of the states. This is intentional. Q1 is the start state, and that's it. Okay, so now the trick is to come up with this recursive structure. Now, how are we going to do the recursive structure? Well, we are going to follow the idea behind Floyd-Warshall. And what do I mean by that? Well, think about all this. Our states are essentially number 1 to n, right? So let's think about all the strings that get us from state I to state j, where the maximum state that is being traveled in the middle is at most k, right? Exactly like we did in Floyd-Warshall, right? And now we will get the recursive definition using this parameter k. So let's define some of those equations. I think it's easier to see it by example. Okay, so Lii0 is essentially you're not allowed to go to any other state, so you're just going to use self loops. So you take all the letters that lead from Qi to itself, and then you have to put cleanest tau, because we can take as many of them as we want. Lij, when I is different than j, is, well, you know, we can stay in I as much as we want. Then we have to take the edge across, right? This is the transition letter. And then we can stay as long as we want in J, right? So we get this equation. Similarly, we can do Lijk. Well, it's either Lijk minus 1, either we don't use the kth state. If we use the kth state, then we have to travel to the kth state without using index k. Then we stay in state k as long as we want, and then we travel back, right? So we get this expression for the language. Lik is again, you have to be careful, so it's Lik minus 1, right? You either stay using state k, or you travel to state k as before, right? So lik k minus 1, lk, you know, stay and go. But then the important thing to observe is that those are all the strings that leads us from I into itself, that are legal, that the maximum state is k, but we can repeat it as many times as we want. So again, we have to put clean star on this. And then of course what we want, Lij, is just Lij of L, when there is no restriction on the maximum state. Okay, so those recursive functions are, you know, those language are well defined. Clearly we can compute it. And of course the important thing is to observe that first one needs to observe that this is really correct. So the proof is by figure. Let's think, for example, on this case, right? Either you go from I to j directly, right? So you take ijk minus 1. Alternatively, you take the k state in the middle, and then you have to go from li to k using k minus 1. Then you can stay in this state as long as you want. This is this string. And then you have to travel to the destination j. So that's how we get this equation. So clearly one can prove the correctness of those things. Let me mention, by the way, that those equations are not easy to derive because you have to be very careful. I do believe that what's written here now is correct, although it took me a while to fix the previous version, which was false or buggy or incorrect. Okay, anyway, the desired language is just the O of the relevant languages. And now we transform the system of equations we had on the languages, we transform them into operation on regular languages, right? Where we do things like, you know, Rijk is either Rijk minus 1 or this. As before, when we deal with the self loop, we need to use the clean star. This is just a direct translation of previous languages. And then you can apply it, right? Because now we have a system, we essentially have this ground zero regular expression, we start building them up, and in the end we will get the regular expression we want. So here's an example how it looks like, right? We first compute the zero regular expression, so this is easy. Right, for state 1, you just, it's B star, for state 2, it's B star, and then if you traverse between them, it's B star AB star, right? So that's easy enough. And then you start putting in the equations, and this is very tedious, but, you know, I have some example of how I did some of them. And it goes on and on and on, but, you know, it's a finite algorithm. In the end, you will get a regular expression that corresponds to the language of the automata as we desired. You know, it's a very mechanical algorithm, but as you would quickly realize, it's exponential time algorithm because the regular expression can be exponentially large in the language, and the correctness, of course, just follows from following the argument of Floyd-Warshall. So it's on one end, it's a very neat algorithm. On the other hand, you can have exponential blow up, which means that in many cases, or most cases, you don't want to do it, right? Which is, by the way, true of all this regular expression stuff, right? We already, when we converted NFA to DFA, we had exponential size explosion. So those algorithms are not necessarily useful, but the important thing is that with regular languages, because we have those 3 different representations, but we understand them quite well, you always can do not whatever you want, but you can usually try and do what you want with a representation that is still compact and useful. Okay, so this is it.